Okay, we'll get started here in about 7 to 8 minutes. Thanks for your patience.
Sweet, I got the book. I've been reading through it.
We'll get started in about 5 minutes. Thanks for your patience. All right, everybody. Thanks for joining in this evening. I'm going to go ahead and share my screen. All right. So you should be seeing the course homepage now. Could somebody verify for me?
Yes, I see it.
Thank you very much. All right. So I have not posted the video from Monday. I do apologize. I was using my laptop at my daughter's house, and so I did not realize that the video actually saved to my Zoom account and not on my laptop. I was looking for it. I thought I had done something wrong, but I found the video in my Zoom account. And so what I'm doing now is I uploaded it to YouTube so that it could be captioned. And as soon as that's done, I will post it in the announcements. So I apologize for the delay. It's just I learned something new about Zoom. I didn't realize that when you use um, a different computer, it actually saves it to your online account. So figured that out. The video will be available shortly. So thanks for your patience on that. So just to kind of recap, on Monday, we looked at Newton's laws. We looked at Newton's 3 laws of motion. And then we looked at some various types of forces that you utilize when you're using Newton's laws to help you understand forces and how they affect motion. So there are a couple of things that I need to do today. One being we're going to deal with the gravitation overview, but I also wanted to remind you that your project article has to be approved by this Saturday, or you lose 20 points on your project score right off the top. Okay, so I don't know, I don't recall right off the top of my head if who has sent me an article for approval, but if you have not, you want to do that as soon as possible. The way you get your article approved is to send me a copy of the article, the full article as a PDF file. You email it to me. I will take a look and tell you whether it's acceptable or not. And you have until 11:59 p.m. this Saturday to get that done. Once that deadline is passed, next week, we'll start the process of talking about the actual summary. And in fact, I'm going to share with you a video in the announcements that will discuss in detail how the particulars of the summary and how I'm going to score it. And that video will be available to you in the announcements, in addition to the information that I'm going to cover with you. So you'll always have that video as a reference if you want to go back and take a look to see, well, exactly what is she looking for, or how is she going to score my summary, so that, I'll put that video out there for you. All right. The other thing I want to mention is that next week is actually midterm week. And you see that your midterm is due by Saturday, the 3rd of July. I hate to impinge on anybody's July 4th plans, but with the 8-week summer course, sometimes you have to cram things in. Now, the good thing is the exam is going to open up this Saturday. It will be available for you this Saturday, and you have until next Saturday to get it done. Okay. I will cover details about the midterm exam next Monday, but it's going to open Saturday. If you want to take a look at the material and you feel comfortable in getting started, feel free. Just be aware that once you open the midterm exam, you have to take it because you're not allowed to go back in. Okay. So, my advice to you is if you're not sure, just wait till Monday when I cover all the information, and then you have more than enough time to get it done. All right. But it does open this Saturday. So I should also make you aware the midterm does not cover anything on Newton's laws. It covers all of the topics prior to Newton's laws. So the nature of science, measurement, unit conversions, 1D motion, vectors, and 2D motion. Those are the topic areas that are relevant for the midterm. Newton's laws is not covered on the midterm, even though we're covering it now. But I didn't put that on the midterm because sometimes the way the calendar falls, I can't cover everything on Newton's law. So I just leave it out of the midterm, and I will pick up that with that topic moving forward on the final exam. Okay. All right. So let me just stop here for a moment. And if you have any questions on anything I said regarding the project and the midterm, please just unmute and ask.
No, thank you. I'm good.
Okay, great. And I will talk about the midterm in detail on Monday. That way, if you take a look at the logistics and what have you, and you have a question before Monday, don't hesitate to reach out to me. I'm always checking my email. Okay. So, I mean, as much as I hate it, it does mean that you will have other items to deal with while you're working through the midterm as well. So that's the downside of an 8-week course. It's just, I have to cram. But, I'm trying to do this in a way that is, so that we can get through what we need to. All right. So gravitation. All right. So we have talked about gravity, but we've talked about gravity from the perspective of acceleration for the most part. We know that on planet Earth, gravity produces an acceleration of negative 9.8 meters per second squared, meaning what? That is 9.8 meters per second squared is the magnitude, and the negative sign tells us that gravity is pointing what? Down. And that's because we typically choose up as positive. Okay. And Monday was the first day that we really hinted at gravity being a force. And we talked about it from the perspective of Newton's second law, where you have to deal with weight. Weight is a force that's present on any object that has mass. And so we find the weight of an object by taking the mass times the gravitational acceleration. So m times g gives us the weight of the object. So we see that gravity does give an object its weight because gravity pulls on that object, exerts a force on that object, and gives the object weight. But that's not the complete picture of how gravity behaves, okay? So we need to dig a little deeper into how gravity works. And to do that, we're going to look at Newton's universal law of gravitation. As we said on Monday, Newton was a pretty special guy because he really gave us lots of insights in terms of how forces work to affect motion and how gravity works, when it's acting on objects or acting between objects, as we'll see. And so to understand gravity from a universal perspective, we need to understand this idea of an inverse square law. We'll take a look at that. And of course, we'll see how gravity interacts and, interacts with objects and creates a force on objects. We'll see how our old formulas for circular motion are relevant for, can be rewritten utilizing gravity. And then we'll look at a couple of sample problems that utilize Newton's law of gravitation. So as it relates to the activities for gravitation, you have a discussion that's due by Saturday. Now, for those three students that are here, no, sorry, I'm mixing you up with lab class. That's not relevant for lecture. So you do have a gravitation discussion that's due Saturday. You have problem set 6 and 7 that are due Saturday. Problem set 6 and 7 deals with Newton's laws that we talked about on Monday. Okay, so that's your opportunity to do some practice problems relating to the topic. Okay. And again, if you run into questions, don't hesitate to reach out to me. I know that you got a lot on your plate this weekend, and I'm going to be paying, extra attention to my email. That way, if I get a question here or there, I'll be responding to you as quickly as possible. And especially since you got to get project articles approved, and not just you, all of my students for all of my classes have to do it by this Saturday. So I'm going to be watching email because I know I got a lot of folk who'll be sending in last minute. So if you send me a question, don't worry about not having access. I'll be paying attention to any questions that you send forward. All right. Here are some materials to help you with the gravitation topic. Chapter 6 in your textbook deals with gravitation. I have some gravitation videos that you can take a look at. And then these are my notes that I'm going to cover with you. Okay. So I'm just waiting for that to come up. I've been having some internet challenges lately. The Cox guy is actually in my front living room as we attempt to have our meeting today, because despite my best effort, we are still having some internet connectivity issues. Hopefully this will come up here in just a moment. If not, I do have a alternate way that I can get to it. I just prefer to use Canvas, but let me try again. Can you see that on the screen? Okay, great. Yeah.
I can see it. Yeah.
Okay. Yeah. I just, because I opened it as a download, I wasn't sure what, that was my alternate way to open it. All right. So let's get into this business of Newton's universal law of gravitation. So as I mentioned on Monday, Newton did this groundbreaking work, this groundbreaking theoretical work to try to get an understanding of how gravity works back in the early 1700s, somewhere along that timeline. And you might have heard the story that, you know, he was sitting under the apple tree, the apple falls, hits him in the head, knocks him out. When he comes to, he says, voila, gravity. Well, that's not totally true. You know, they've kind of sensationalized that story a bit, but it is true that he had a particular revelation while watching an object fall. So he began to reason that if the object is falling from a stationary position, so imagine the apple is sitting in the apple tree, not moving, and then all of a sudden it starts to fall. Well, that automatically means that the apple is accelerating. Because if it goes from 0 to something, it accelerated. So he reasons that if that apple is accelerating, there must be a net external force acting on it, right? Because his second law says if an object is accelerating, it's because it's being exposed to a net force. But here's the thing. He didn't see anything pushing or pulling on that apple. So this is some kind of force where objects can accelerate because of it, but you don't readily see the object being pushed or pulled. You know, you don't see anything touching the object as we typically think of pushing or pulling in the classic sense, right? So in his mind, there's this invisible force that can make objects accelerate. And so he begins an investigation. And what he finds out is that there's this force that he called gravity that can cause objects to be attracted to one another. In fact, he comes up with this universal law of gravitation that says every particle in the universe attracts every other particle in the universe. So any two objects in the universe are pulling on each other, pulling each other, you know, attracting each other toward each other. Now, I don't know, you know, I mean, we might take that for granted today because gravity is like this thing we just, you know, we wake up understanding how it works. But imagine back then, the idea of Newton being able to say that I have uncovered a force, and the way this force behaves is that throughout the entire universe, most of which we didn't know anything about, throughout the entire universe, I can pick any two particles and tell you how that force behaves. That's pretty incredible for him to be able to propose that, right? Now, he was smart enough that he wouldn't propose something like that without having the mathematics somewhat worked out to explain it. And so what he figured out is that if we pick any two objects, call them M, little m, and big M. These are two masses, little m and big M. So the bigger those two masses are, the bigger that force, that attractive force, gravity, between them. Okay? So as the masses get bigger, this force of attraction, gravity, gets bigger. he also works out that this force of attraction gets weaker as the objects get further apart. Okay, but here's the thing. He figures out that this force diminishes as they get further apart, but you have to take that distance and square it to see how that force changes. So it's not a 1-for-1. It's 1 over the distance squared, what we call an inverse square law. So this force of attraction between objects is directly proportional to the product of the masses, but inversely proportional to the distance between them squared. Now you might see the equation that's written on the screen. F, which stands for the gravitational force, equals big G. This is the gravitation constant, and I'll talk about that in just a moment. And then you take the two masses and you multiply them, and you divide by the distance between them squared. Now here's the thing. Newton didn't totally come up with this equation. He saw the proportionality between the masses multiplied and the proportionality between 1 over the distance squared. But the reason he could not complete the equation, an equation says equal to. Well, he wasn't able to say definitively equal to. And that is because during his lifetime, we did not know the mass of the earth. So, picture in your mind, the biggest object around us is the earth. And so because he didn't know the mass, he could see that objects were attracted to the earth, but he couldn't directly work out that equation because he needed to know the mass of the earth. Well, 100 years after Newton, a fellow named Henry Cavendish does an experiment to find the actual completed equation, because 100 years later, we did know the mass of the earth. And so Henry Cavendish is able to take what Newton found in terms of proportionality and take that a step further and write it in terms of an equality. So Newton was able to figure out the relationship between the masses and the distance. Cavendish was able to find the equality dealing with the masses and the distance squared. And to write it as an equality, he had to utilize this big G, this gravitational constant. Now, I mentioned to you on Monday that gravity is one of the weakest forces of the 4 fundamental forces, right? And somebody asked me a question, why is it like that? So let me show you something here, the reason why it's like that. Okay, because I thought about that question, and I wanted to be able to give a more inclusive answer. And so now that we're looking at this gravitation law here, F equals big G M, and sometimes you see textbooks that write it M1 and M2, but I'm going to follow the notation in the notes over R squared. And the unit for force is the Newton. Okay. Now, we owe to Henry Cavendish this big G, which he was able to work out experimentally. And it is, most often you see it written 6.67 times 10 to the negative 11. Newton meter squared over kilogram squared. That's the unit. Okay. Now, you can look at this constant, this gravitation constant. Sometimes you hear us use the math term, this constant of proportionality, which allows us to take a proportional to and write an equal to. You can see that it's extremely small, times 10 to the minus 11, 0.00000, all of those zeros, 10 to the minus 11, right? That's an extremely small value, which tells you that naturally gravity is extremely weak. The way you feel gravity is because you have to have, you know, objects that are fairly big in size and fairly close together. Well, which big object are you closest to? Earth. So that's why in your mind and in your experience, gravity is not weak at all because it's keeping you fixed to the planet, right? But technically, it's a very weak force because if the Earth was a much smaller object, you wouldn't even notice it. For example, right now you're sitting in front of a computer screen. And if you put your mass there and the mass of the computer divided by the distance between you squared, that the product of those two masses isn't going to come close to dealing with this 10 to the minus 11. You need a big number to take care of this small exponent. I mean, this, extremely small value here, right? Let's say, for example, that your computer has a mass of 10 kilograms, and let's say that you have a mass of 100 kilograms. That's 1,000, right? 10 times 100 is 1,000. And let's say you're 1 meter apart. There's a meter difference between you and your computer screen, which is probably not the case, but let's make it simple. So that's 1,000. 1,000 times this 10 to the minus 11 is going to be negligible. So there's no chance that when you sit in front of your computer screen, it's going to be attracted to you and smack you in the face because the force of attraction is not big enough to do that. But now a big planet like the Earth, yeah, it could keep you, it could hold you down because the mass of the Earth is 6 times 10 to the 24. Well, 10 to the 24 will take care of this, right? And so you feel the Earth pulling on you. Okay? And so, when we think about the power of this equation allows us to figure out the force of gravity, the force of attraction between any two objects if we know their mass and how far apart they are. Thanks to the work of Sir Isaac Newton and Henry Cavendish. Now, there is a much more complicated form of gravity that Einstein was, worked out and proposed. But we don't really get into relativity in this class, right? For the things that we're going to deal with, this law is more than appropriate. But I did tell you that a law has its limitations, right? Newton's law only works, when we're dealing with everyday kinds of objects, a planet, a car, people, apples, everyday objects. And so we don't need to worry about relativistic effects when we deal with this equation. And Einstein was able to figure out that, hey, you know, Newton did a pretty good job, you know. Um, Cavendish comes along 100 years later and gives us this proportionality constant. Einstein comes along 100 years later, and through his work, he's able to say that, yeah, you know, this 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 law is consistent with what I'm seeing as well. Because in fact, watch this trick. If we take this out and we take big G times the mass of the earth divided by the radius of the earth, radius of the earth squared, it gives us 9.8 meters per second squared. So you see here that is very much consistent with the idea that an object's weight is equal to the object's mass times G. Because what is that? That is equal to G on planet Earth, right? That's one, think about it. Now, if I can use this to get the gravitational acceleration on Earth, then what if I put the mass of the moon and the radius of the moon in there? Then I can get the gravity on the moon or whatever other planet I want to know about, right? So see, this is right here how Einstein was able to verify that Newton was on the right path, because this gives us a value that we know very well. Okay. Now, you might be thinking, well, hey, wait a minute. If this equation gives me the same, you know, value as the weight, then why do I need to use this? Why don't I just do mg, right? If all this stuff on planet Earth equals to 9.8, and if I take an object's mass times g, I get the object's weight, what is the benefit of this equation? Here's a very important benefit. The moment you step off planet Earth, you can't use this anymore because you're not on planet Earth. So the beauty of Newton's universal law of gravitation is it allows me to find the force of attraction between any two objects anywhere in the universe, not just on the planet. So for example, if you're flying in a jet 40,000 feet above the surface of the Earth, you can't use 9.8, but you can use this formula, because you know the mass of the Earth, you know the mass of the jet, you know how far away from the Earth it is. So you can figure out how much that jet is going to be pulled on by planet Earth. Or what if you're a passenger in that jet? You can figure out how much the Earth is pulling on you while you're riding in that jet. Because you can't do, see, your weight is how much the Earth is pulling on you if you're on the planet. But if you're not on the planet, you need to go to the gravitation formula to figure out how much force of attraction. Okay? So that's the beauty of being able to use the universal law of gravitation. All right? Because it allows you to truly figure out the gravity force anywhere in the universe between any two objects in the universe. Okay? Any question about that? Because, I mean, that's a pretty powerful statement. I want to make sure you understand the usefulness of that statement.
Not sure I understand.
Say again.
Not sure I understand.
Okay, let's look at an example that hopefully will clarify. Okay. Let's see here. So I'm going to go in the announcements and I'm going to go into, remember I gave you some extra resources. And so I'm going into the extra resources. So here, there's a bunch of things on gravitation here, but let's take a look at an example. Okay. So it says, determine the force of gravitational attraction between the Earth and a 70 kilogram physics student if the student is standing at sea level. Okay. So let's imagine you are the 70 kilogram physics student and you're standing at sea level on planet Earth. So how far are you away from the center of the Earth? Because that's what you have to do, right? You have to measure from the center of each object. So if we measure from your center to the center of the Earth, this distance is 6.38 times 10 to the 6 meters. Because the radius of the Earth is so big that, you know, the distance from your belly button to the surface of the Earth is like negligible compared to the radius of the Earth. All right. So the distance between you, if you're standing on the Earth at sea level, is 6.38 times 10 to the 6 meters. We know your mass, we know the mass of the Earth. So let's figure out how much gravitational attraction. So I plugged in big G, because remember the formula has what? Big G, the mass of each object divided by the distance squared, right? So here is big G, here's the mass of the Earth, here's your mass, 70 kilograms, and here's the distance squared. So what I did was I put out all the numbers because I don't have one of those fancy calculators where I can do grouping and all that. So I do it the old-fashioned way. I multiply all my numbers first, and then I do all my exponents. So 6.673 times 5.98 times 70 divided by 6.38 squared gives me 68.6. And I do the exponents, 10 to the minus 11, 10 to the positive 24, divided by 10 to the 6 squared. Now, let me just play around with this just for a minute. Do you realize that if this number is not so big, then this number is going to dominate? So you need a big object like the Earth that has a big exponent to cancel out this exponent, okay? Because when I take 10 to the 24 times 10 to the negative 11, I get 10 to the 13, because you have to add the exponents. And then when I divide by 10 to the 6 squared, that becomes 10 to the 12, okay? Because when you multiply when you raise an exponent to a power, you have to multiply. Now I'm dividing 10 to the 13 divided by 10 to the 12. That gives me 10 to the 1. So 68.6 times 10 to the 1, or 10, gives me 686 newtons. So this student that's 70 kilograms, that's standing at sea level, is being pulled by the Earth, is being attracted to the Earth with 686 newtons of force. Let's figure out this student's weight. If they're standing at sea level, let's figure out the student's weight. How do we do that? Mass times gravity, right? So 70 kilograms times 9.8 meters per second squared, because we're on Earth. If you multiply that out, guess what you get? 686 newtons. So if the student is standing on the earth, we can get their weight by taking mass times gravity, or we can use Newton's universal law of gravitation. They both are equivalent. Do you follow that?
Yes.
Okay, now let's take a look at another example, because this will highlight for you what I mean when I say, well, we can't use mass times gravity in this case. Watch. Determine the force of gravitational attraction between the earth and the 70 kilogram student if the student is in an airplane 40,000 feet above the earth's surface. So now they're not on the planet. So we cannot do W equals mg. We can't take mass times gravity. Why? Because they aren't on the earth. They're 40,000 feet above the earth. 9.8 only works if you're on the earth. But we can still use Newton's universal law of gravitation. Why? Because he doesn't care where you're at. Because the formula says take the distance between you. Now they're 6.39 times 10 to the 6 meters from the Earth's center. Because we had to add the 40,000 feet to the radius of the Earth, right? Okay, if they were on the surface of the Earth, we use the radius of the Earth. But since they're 40,000 feet above the Earth, we have to add that distance to the radius to figure out how far away they are from the center of the Earth. Does that make sense to you?
Yes.
Okay, so now we're substituting our numbers in, right? Big G, the mass of the Earth, the mass of the student. That hadn't changed. But what has changed is the distance they are from the center of the Earth. So let's go through the process. There are our numbers: 6.673, 5.98, 70, 6.39 squared. What do I get when I do that? 68.4. My exponents work out the same, right? Time 10 to the 1. So now 684 newtons. You see, when they're on Earth, the Earth pulls with 686 newtons. When they're riding 40,000 feet above the Earth only pulls with 684 newtons. And we wouldn't get this value if we did W equals mg. Okay, so the beauty of this formula is that we can find the force of attraction between any two objects, whether it's the Earth and a student, whether it's two apples, whether it's the moon and Jupiter, any two objects, as long as we know their masses and how far apart they are. So this is truly powerful because it expands our understanding of how gravity works beyond the planet Earth to objects everywhere in the universe. That is the power of Newton's universal law of gravitation. All right. So does that make sense to you?
Yes.
Okay, great. Because I definitely wanted to get those two examples in, because it's important not only to know the law, but to know how to apply it. That's the beauty of it, is in what we can use it for. All right. So now we know, one of the most obvious examples of this force of attraction between objects is the attraction between the moon and the oceans on the earth. And that's the tides. We know, we hear on, high tide and low tide. We know, for example, that if a hurricane's coming and it makes landfall during high tide, that's going to be a problem, right? You're going to have a much bigger storm surge, right? Well, why do we have this high tide and low tide? That's the result of the gravitational attraction between the moon and the oceans on the earth. Okay, so that's one example of this, utilization of the law of gravitation. Another application that you hear folks say sometimes is this idea of weightlessness. Now, let me just be very clear with you. Weightlessness is a sensation. It's like, it feels like an object might feel like it's weightless, but it's not actually weightless. You hear people say this idea of zero gravity, or truly, if we're following what Newton's universal law of gravitation says, there's no such thing as zero gravity. There's microgravity, meaning that there's a small value.
I have a question.
Yeah.
What do you mean by, like, if there was no gravity, wouldn't that mean that everything just
No, I'm not saying there's no gravity. I'm saying that there is no situation where there's no gravity, because Newton's universal law says that all objects are pulling on each other, right? So there is gravity, right? It's just that the gravity is so much smaller, it feels like this idea of a zero gravity, right? Feels like it means that it's a sensation, but it's not real. Okay? So when an astronaut is in a spacecraft and you see that they're floating all around, because there is reduced gravity, but there is not zero gravity. And they are not weightless, and neither are any of the objects on that spacecraft. They are feeling that sensation because the craft that they're in is free falling around the earth. So the spacecraft is free falling. They are inside the spacecraft free falling, so they feel weightlessness, but they aren't actually weightless. And there is actually gravity. Okay? So,
yes.
yes,
That makes more
that
sense.
makes sense. Absolutely good. Great. Okay. All right. So these are some phenomena that you come across when people talk about gravitation. And so I want you to be aware of that. All right. So I mentioned on Monday that one of the scientists that Newton relied on when finding his law of gravitation was Kepler. So he utilized the work of Galileo to come up with his 3 laws of motion. He utilized the work of Kepler to come up with his law of gravitation. And, truthfully, human beings have always been interested in the planets. That we have evidence of early cultures, even before the Greeks, that knew about the planets and stars. Because of the strong historical record left by the Greeks, we know that folk like Ptolemy and others were interested in trying to explain the motion of the planets. Well, Kepler comes along, and you can see that he was before Newton's time. right? Newton was born in 1642. So Kepler, dies 12 years before Newton comes along, right? Newton's born. So Kepler was a planet fanatic, for lack of a better expression. He wanted to know everything about the planets. So he did a great many observations of the planets, right? He knew things about their orbits, and finding out that the orbits were elliptical, and finding how fast the planets moved, how much area they swept out, the periods, all of those things. He did a lot of data collection, and he synthesized his observation and data in the form of what we call Kepler's 3 laws of planetary motion. Now, I'm not interested in you knowing Kepler's laws. I do want you to realize that Newton used Kepler's laws to come up with the law of gravitation. In particular, this third law. Kepler's third law looked at the ratio of the periods, the square of the periods to the ratio of the cube of the distance from the sun. Okay, and so Newton. Remember, I told you Newton is doing this work to find the law of gravitation theoretically. He's not doing any experiments. He's working through this mathematically. And so, he uses the work that Kepler did to help him come up with the law of gravitation. And in your mind, you might be thinking, well, if Kepler had all that data, why didn't he come up with the law? Well, that's a very good question, because Kepler knew everything about the planets except one very vital piece of information: why they orbited. He knew everything about their orbits, but he couldn't tell you why they orbited. What was keeping them in orbit? He had no way to explain that. And so this is why Newton's universal law of gravitation is extremely powerful, because it takes Kepler's laws and expands on them and explains that it's gravity that is keeping the planets in orbit. So while working out this idea of gravitation, Newton theorizes that the same gravity force that makes apples fall to the earth keeps the planets in orbit. And then he goes about mathematically showing how it works. That's extremely powerful. Okay. And this law was key because he could see from this mathematics, he used this mathematics and built on it to come up with the law of gravitation. Okay. All right. So I think, let's see, I want to make sure that I didn't leave anything out there, because I did say that I wanted to work some examples for you, and I've done that. There is one more thing that I want to do in these notes, and that is to show you how the information that we learned about circular motion can now be, I want to say, looked at in a different way. Okay. So if you recall, when we talked about 2D motion and we talked about objects moving in a circle, like an orbit, like a satellite, for example, orbiting the Earth, we talked about how we can find out how fast that object is orbiting and the acceleration. And To find out how fast the object is orbiting, we can use 2 pi r over t, where r is the radius, the orbit radius, and t is the period. The period means how much time it takes to make one complete trip around, okay? And so if we utilize this value, we know how fast the object is orbiting, because remember, these objects are moving into a two-dimensional circle, two-dimensional, right? So that speed is fixed. But you remember, I mentioned to you that because the direction is changing, we produce an acceleration. And the size of that acceleration can be found by taking this speed, squaring it, and dividing by the orbit radius. So we can figure out how fast an object that's orbiting the Earth, for example, uniformly, constant speed, by doing 2 pi r over t, and we can find out the acceleration by doing v squared over r. Now, if this object is in orbit around the Earth, what's keeping it in orbit? Gravity. And so we can go to Newton's universal law of gravitation to provide an alternate way of looking at this circular motion, orbit motion that is being produced by gravity, right? Because, you know, if somebody finds the gravity button or the gravity switch and turns gravity off, then these objects, these satellites aren't going to be able to stay in orbit anymore, right? That's the idea. So we can look at this from a perspective of circular motion, or we can look at it from the perspective of gravitation motion. Why? Because gravity is making it stay in this circular orbit. All right. Now we can build on our Newton's second law, force equals mass times acceleration, and simply substitute this v squared over r for our acceleration.
I'm sorry, can you say that one more time? The interpreter missed it.
No problem, no problem. So we know from Newton's second law on Monday, force equals mass times acceleration. But for an object that's orbiting in a circle, that acceleration is the centripetal acceleration, meaning it's the acceleration that that object feels toward the Earth, because it's being pulled toward the Earth. It's being accelerated toward the Earth, okay? And so if force is equal to mass times acceleration, we can simply substitute v squared over r for the acceleration. And so now we have a way using our circular motion to figure out the amount of centripetal force that the orbiting object feels. So let me break that down in terms of a real example. Right now, there's a satellite called the International Space Station. The International Space Station is a satellite that is orbiting Earth. It is approximately, excuse me, approximately 100 miles above the Earth's surface, give or take, okay? And because that object is going in a circle around the Earth, it's being pulled in toward the center of the Earth. Fortunately, that satellite has a forward speed that keeps it from crashing into the Earth. That forward speed, 2 pi r over t, counteracts that centripetal acceleration or that force toward the center of the Earth, and it allows the satellite to stay in orbit. Okay? So that's just explaining the orbit motion using our old circular motion concepts. Circular velocity or speed, centripetal acceleration. Now we can add centripetal force. or we can look at it from the perspective of gravity. Because again, what is producing all of this? Gravity is producing that orbit. Without gravity, that International Space Station won't stay in orbit. Okay? So we can take Newton's universal law of gravitation, do some algebra, which I will never ask you to reproduce because it is a bit complicated. And here's another way we can find out how fast the satellite orbits around the Earth. Okay, so I can use this formula, 2 pi r over t, or I can use this formula, square root of big G times big M over R, where big M is the mass of the planet, in this case, the planet Earth. Now, pay particular attention to this formula, because if you look at either one of them, notice the mass of the object, in this case, the mass of the International Space Station, is nowhere in the formula. How fast the satellite orbits does not depend on its mass. What does it depend on? It depends on the mass of the planet and how far away it is from the center of the planet. Okay, so that's pretty powerful. We can put up a satellite of any mass out there, and as long as we put it at the right distance, it's gonna, we can figure out how fast it's going. Okay. We can also utilize Newton's universal law of gravitation to figure out an alternate form for the centripetal acceleration. And that is big G over big M divided by R squared. So we got two ways to figure out how much acceleration. We can do it using our circular motion formula, or we can do it using our gravitation formula. Okay? And that is because orbit motion is directly impacted by gravity. Okay? And then you see here on the bottom, and I do apologize, it's a little bit difficult to see, but you see here, the other important formula relates the period to the orbit radius. So the period squared is equal to the orbit radius cubed. Remember, the period is the amount of time it takes to go around once, and the orbit radius is how far away it is from the center of the planet. Okay? This is Kepler's law. This last formula is Kepler's law. And this is what Newton took to build on to find his law of gravitation. All right. So let's see here. I have one more example that I want to share with you. Let me do this. Let me do this right here. That's not what I want. Okay, and I'll go back into 2D motion notes, because this is an example of how we can utilize our understanding of circular motion to figure out how fast, for example, this GEO satellite is orbiting the Earth. Okay, so this GEO satellite, and I don't know if I worked this example for you last week, but I'm going to take a moment and do it now, because I want you to see that this idea of orbit motion is, is pretty important. And not only that, it's a realistic example because we have a lot of satellites orbiting the Earth now. I mean, thousands of them. If you you know, pay attention to any of the kind of reports by NASA and those other organizations. I mean, there are thousands of satellites out there. Communication satellites, spy satellites, you name it. They got them out there. All right. And so let's take a look at this type of satellite. It's a geo satellite, geosynchronous satellite. And so what this geosynchronous satellite does is it rotates around the Earth once every day. So it makes a complete trip around the Earth in, you know, a complete trip in 24 hours. Okay. So it is literally staying aligned with a particular point on the Earth's surface. And as that, you know, the Earth makes one complete trip every 24 hours, right, on its axis. And so this satellite is staying fixed above a point on the Earth's surface. It's literally following that point as it orbits. Okay. And so, and this type of satellite, this geo satellite, it orbits approximately 22,000 miles above the Earth's surface. So if you're standing on the Earth's surface and you look 22,000 miles out, this is where you'll spot this type of satellite. Okay, which means if we measure from the center of the Earth, that's about 26,000 miles. Because remember, when we are finding the orbit radius, we have to measure from the center, not from the surface. Okay, the radius of the Earth is about 4,000 miles. So if we add 4,000 to 22,000, we get 26,000. Okay, and so let's figure out how fast it's going and how much acceleration. So to find how fast it's going, the orbit speed, the tangential speed, we have to take the distance, which is the circumference, divided by the period. Okay, so how far does it go in one trip? 2 pi r. How much time does it take? That's the period t. So 2 times pi times r. R is 26,000. T is 24, right? Because this satellite makes a complete trip in 24 hours and is about 26,000 miles from the center of the Earth. When we multiply that out, this satellite, this geo satellite, is moving at about 6,800 miles per hour. 6,800 miles per hour. Now, think about it. The fastest car we on planet Earth, if it's going 500 miles per hour, even a jet that's going 500 miles per hour, is not going to be moving nearly as fast as this satellite. 6,800 miles per hour, right about. Okay. These geo satellites, these are like your communication satellite, like Verizon or T-Mobile, not T-Mobile because their stuff doesn't work very good. You know, or your news station, you know, those types of satellites. They're about 22,000 miles from the Earth's surface, right? And they're going at about 6,800 miles per hour. Notice that has nothing to do with the mass of the satellite. How fast it goes, that has nothing to do with its size. Okay, let's figure out how much acceleration. So we have to take this speed, 6,803 miles per hour, square it, and then divide by the radius. So square 6,803, you have to also be careful to square the unit, miles per hour. That has to get squared as well. And then you divide that by 26,000 miles. So you get an acceleration. Remember, this centripetal acceleration is how much the satellite is being accelerated toward the center of the earth. So when you do the math here, you get 1780 miles per hour squared. Okay. And of course I rounded to a whole number there, but you can see that's I did this in miles per hour because I figured that's a unit that you can relate to, because, if you're driving your car 70 miles per hour, you're not anywhere near this speed. Okay. All right, let's take a look at a LEO satellite. So a LEO satellite is a low Earth orbit satellite. So the International Space Station is an example of a LEO. Okay. The International Space Station is a satellite that's orbiting the Earth. There are people living on it right now. They're doing all types of scientific experiments to eventually help us move even deeper into space, right? Because if we're going to do that, we need to know what are going to be the long-term effects on the human body, on plants, on materials. There's so much that we need to know before we can, humans can actually live permanently in somewhere else besides planet Earth. So there are people that are living on the International Space Station, sometimes for 6 months to a year, even up to 18 months at a time. Okay. And I tell students, these people are living on the International Space Station. Their zip code is SPACE. All right. So now let's see how fast a LEO satellite is moving. A LEO satellite is orbiting at approximately 100 miles above the Earth. It makes a complete trip every 90 minutes or an hour and a half or 1.5 hours. Okay. And so it's 100 miles above the Earth. So we had to add that 100 miles to the radius of the Earth. And so that's approximately 4,060 miles. The orbit radius is about 4,060 miles. The period is 1.5 hours. So when you plug that into the formula, 2 times pi times r divided by 1.5, you get 16,998 miles per hour. Almost 17,000 miles per hour. That's much, much faster than a GEO. I mean, 17,000 miles every hour. That's an incredible speed. Okay. And then we can figure out the amount of acceleration that's being felt by that satellite. V squared over R. So take 16,998 miles per hour, square all of that, the number and the unit, and then divide by 4,060 miles. You get a centripetal acceleration, 71,166 miles per hour squared. Speed is measured in miles per hour, acceleration, miles per hour squared. Okay. So you can look at this two ways. This satellite is being accelerated at a very high rate toward the center of the Earth. So it has to have a very big speed to help it stay in orbit. Remember that forward speed is what counteracts this acceleration to keep the object in orbit. You could also look at it this way. Because this object is moving around the Earth so fast, it is being pulled toward the Earth much more. Okay, so you can take this concept of orbit and think about our planet Earth going around the sun. So the Earth is going, we make a trip, every 365 days, right, around the sun. Now, the orbit around the sun is not a circle, it's elliptical. But, I always say we can estimate, right? We can approximate. we can approximate the Earth's orbit around the sun as a circle. And think about, if the Earth did not have an extremely large forward speed, it would get accelerated into the sun. Because the Earth is experiencing an extremely high centripetal acceleration, but it also has an extremely high forward speed. So we hope that the Earth will maintain that forward speed and not someday slow down to the point where gravity will take over and just send the Earth on a spiral into the sun. Why? Gravity. Gravity is what's keeping the Earth in orbit. It is what's producing that acceleration. But we hope the Earth has a real strong motor and it keeps that forward speed so that that gravitational attraction doesn't win out. Okay? So does that make sense to you? If you have a question, please don't hesitate to unmute, ask a question. I'll be happy to address any question that you might have. So I'm going to stop the share and let's see. So I take it from the silence that everybody's good. Okay. All right. So that concludes our class.
I think some practice will make it a little bit better too.
Say again, ma'am.
I think some practice will make it a little bit better too.
Yeah, well, he'll definitely have an opportunity to do that on the problem sets. Okay. All right, so that'll conclude our class for today. I'll see you back here Monday, 5:30. I'll be posting the recording from Monday and this recording so that you have access to it, along with a video that deals with the project. And don't forget, you have access to the examples that I worked on gravitation through the announcements, but I'll also put a link for that in the announcements when I post the video so that you can go directly to them if you want to.
All right.
All right. Y'all take care.